All right, welcome back everyone to the deep dive. Today we're going to try to get to the bottom of something I think we all take for granted, electrical circuits and power sources.
Yeah, you don't really think about them, until the power's out.
Exactly. So we've got all this material here, explanations and diagrams, all about how electricity really works, how it flows, what makes it flow, and all the different ways to generate that power.
It's amazing how much our modern lives depend on this stuff. It's everywhere.
Yeah, you really don't think about it until it's gone, like you said. And even then, I'm not sure most people know how it all actually works. So we're going to go through all of this, and by the time we're done, I hope, we'll have a much better understanding of how electricity really works. We'll even try to answer some practice questions at the end to see how well we
That's
do.
good. Let's dive in.
All right, so section 3.1 here, the intro, gives us a rundown of what an electrical circuit even is.
Yeah, the basics. What are the parts? How does it work?
Yeah, how do electrons move? What gets them moving? All the different types of power sources. It's like a foundation, a starting point, before we can really get into the details.
I like that, building a foundation.
So section 3.2 jumps right into it. The electrical circuit. So we've got a power source, right? And that power source is like the heart of the whole thing. It pushes and pulls the electrons, gets them moving through the circuit.
Creates that flow of electrical energy.
Yeah. And that flow, that's what we call electricity. And there's this really helpful diagram here, figure 331. It shows the whole loop, the power source, the conductive path, that's the wire.
Wires there.
Then you've got the appliance, the thing that's using the electricity, which they call the load. And then another wire takes it all the way back to the power source. It's a closed loop, right?
Yeah, a complete circuit.
Like a circle. And the electrons, those little guys, they leave the power source, they do their thing in the appliance, whatever it is, like making a light bulb light up or running a motor, and then they go right back to the power source to get re-energized.
It's like a continuous loop, right? If there's a break in the loop, if the circuit isn't complete, the electrons stop flowing.
Exactly. And that's when things stop working.
All right, so now let's talk about how these electrons actually flow. Section 3.3, electric current flow. And this is where it gets interesting.
Interesting how.
Well, there's actually two different theories about which way the electrons move.
Two theories.
Two theories. It's like two different ways of looking at the same thing.
Okay.
So the first one is called conventional current flow theory. And this goes all the way back to Benjamin Franklin in 1752.
Oh, wow. That's going way back.
Yeah. So based on his experiments with static electricity, rubbing a balloon on your hair kind of stuff,
Yeah.
he figured that current flowed from positive to negative.
Positive to negative. Okay.
And figure 3.2 here, it shows that idea visually. The arrows go from the positive terminal of the power source through the appliance and then back to the negative terminal.
So the current is flowing from plus to minus.
Yeah, in this theory. But hold on, because there's another theory.
There's more. Yep. The second one is called electron current flow theory. And this one came about after J.J. Thomson discovered the electron in 1897.
Oh, so later.
Way later. So his experiments showed that electrons, which are negatively charged particles, actually flow from negative to positive.
Oh, so the opposite direction.
Exactly. So figure 3.3 shows this. You can see the electrons leaving the negative terminal, going through the appliance, and ending up at the positive terminal.
So which one is right?
Well, both theories are still used in different ways, but the author's comment here points out that the electron current flow theory is considered more accurate. It's what's really happening with the electrons.
So the electrons are actually moving from negative to positive. Got it.
Okay, ready to move on.
I think so, yeah.
All right, now for the real meat of the matter, electrical power sources. That's section 3.4. So the basic idea here is that a power source, any power source, is what provides the energy to make the electrons move in the first place.
Yeah, that makes sense.
It gives them the oomph to leave their atoms and start flowing through the circuit. And this energy, it can come from all sorts of places. Chemical reactions, electromagnetism, light, heat, even pressure.
Wow. Lots of options.
Right. It's really quite amazing when you think about it.
Yeah, a lot of different ways to make electricity.
Okay, let's break it down, starting with chemical activity. So we've got batteries. Right.
Those are pretty common.
Yeah, they are. And a battery is basically stored chemical energy. It's made of one or more of these things called voltaic cells.
Voltaic cells.
Each cell has a positive side and a negative side. And if you have a battery with multiple cells, like a car battery, the positive side of one cell is connected to the negative side of the next one.
Okay.
And figure 3 to 5 shows us this really well. You can see a car battery with its multiple cells, and then some smaller batteries like the ones you'd find in a flashlight or something, which are single cell batteries. and they all have those positive and negative terminals.
Makes sense.
And fun fact, Alessandro Volta, the guy who invented the voltaic cell, he did that back in 1800.
That's a while ago.
It is. So let's talk about how a battery is actually put together, the battery construction.
Okay.
You've got three main parts: the electrolyte, the anode, and the cathode.
Electrolyte, anode, cathode.
The electrolyte, that's the chemical stuff that's inside the battery. It's the medium where the electrons can move around.
The juice.
Yeah. The anode is the negative terminal, and the cathode is the positive terminal. And figure 3 to 6 shows a cutaway view of a battery cell, so you can see all those parts.
Cool. So how does it actually work?
All right, so that's the next part. Electrical pressure in a battery.
I'm ready.
Basically, the chemical activity happening in the battery, especially at the negative terminal, causes a bunch of electrons to build up there.
They get crowded, huh?
Exactly. It's like they're all pushing and shoving to get away from each other, and that creates pressure, an electrical pressure, between the positive and negative terminals.
It's like a difference in water level between two tanks.
Exactly like that. So if there's a conductive path, a wire connecting those two terminals, those electrons are going to flow from the negative side to the positive side, trying to even things out.
Makes sense. They're looking for space.
Yeah, they want to spread out. And that flow, because it always goes in the same direction, negative to positive, that's what we call direct current, or DC. Figure 3 to 8 shows this really well.
Always going one way?
Always one way, that's DC.
Okay, so that's how batteries work.
That's how batteries work. Now let's switch gears a bit and talk about another way to generate electricity: electromagnetism.
Magnets.
Yeah, basically. This is actually how most of our electricity is generated, on a large scale.
Really?
Yeah. It uses magnets and coils of wire and motion to create electricity.
Okay, I'm intrigued.
So figure 3 to 9 shows a simplified diagram of an alternating current generator, or an AC generator. It's a bit complicated, but the basic idea is that you have a prime mover. That could be a steam turbine, a wind turbine, anything that can spin a shaft. And that spinning shaft, it makes a magnet rotate inside a bunch of coils of wire. And that spinning, that motion, it creates a changing magnetic field, which induces an electric current in the wires.
Oh, wow. So the spinning makes electricity.
Yeah, exactly. And because the magnet is spinning back and forth, the current it creates also alternates directions, and that's why it's called alternating current, or AC.
Oh, right, because the electrons are going back and forth.
Exactly, and that's the kind of electricity that comes out of your wall outlets.
Makes sense.
All right, ready for another way to make electricity?
I think so. Let's hear it.
This one's called photoelectricity. Have you heard of that?
I think so, but I don't really know what it is.
So this is all about turning light into electricity.
Light. Really?
Really? So you know how solar panels work, right?
Well, I mean, I know they use sunlight, but that's about it.
Yeah, so that's photoelectricity in action. When light hits certain materials, like silicon, it can knock electrons loose and create an electric current.
Oh, wow. That's pretty cool.
Yeah, it is. Figure 310 shows a diagram of a solar panel. You can see the light hitting the solar cell, which is made of special layers of silicon, and how that causes the electrons to start moving.
It's like the light is giving the electrons a little kick, right?
Exactly. So that's how solar power works. It's pretty amazing.
That is pretty cool.
All right, on to the next one. Thermoelectricity.
Thermoelectricity.
Yeah. So this is all about turning heat into electricity.
Heat.
Heat. If you heat up the spot where two different metals touch, it can cause electrons to flow and create a voltage. Figure 311 shows a diagram of this.
So like just from the heat itself.
Yeah, from the heat.
Yeah.
It's pretty wild.
Yeah.
And a common application of this is in a device called a thermocouple.
A thermocouple.
Yeah, it's basically a temperature sensor. Figure 312 shows some examples. You have two different metals joined together, and when you heat or cool that junction, it creates a voltage that you can measure. And the amount of voltage depends on the temperature, so you can use it to measure how hot or cold something is.
I've never heard of that before.
They're used all over the place, in factories, in science labs, all sorts of places where you need to measure temperature accurately.
Okay.
And last but not least, we have piezoelectricity.
Piezoelectricity. Now that's a new word.
I know, right? It's a mouthful. But it's actually pretty simple. It's all about turning pressure or vibration into electricity.
How do you do that?
So certain materials, like quartz crystals, have this property. When you squeeze them or put pressure on them, they generate a voltage.
Wow, really?
Yep. Figure 313 shows a cool example. It's a pressure spark device, like the kind you find in some lighters. You press a button, and it smacks a crystal, and that creates a spark to light the gas.
So just by pressing on it, you create electricity.
Exactly. And that's piezoelectricity.
Wow. So we've got batteries, generators, solar panels, thermocouples, and these pressure spark things. It's amazing how many ways there are to make electricity.
It really is, and each one has its own advantages and disadvantages. Okay, are you ready to test our knowledge with the practice questions?
I think so. Bring it on.
All right. Question 1. In an electrical circuit, the electrons leave the power source on a Kalyan path traveling toward a load and then return to the power source. The answer is A, conductive.
Conductive. Yeah, that makes sense. It needs to be something that lets the electrons flow easily.
Yeah, like a wire.
Right.
Okay, question 2. The rate of electron flow is explained by one of two theories, the conventional current flow theory or the electron current flow theory. The rate of electron flow is C. The answer is C.
Current. Yeah, that's how many electrons are moving past a point per second, right?
That's right. Question 3. According to the current flow theory, Benjamin Franklin discovered that electricity flows from a positive charge to a negative charge. The answer is A, conventional.
Conventional. Okay, that was Franklin's idea, right?
Yep, positive to negative.
Even though we know now it's the other way around.
Exactly. Question 4. According to the conventional current flow theory, Benjamin Franklin theorized that electric current flowed out of the terminal through the circuit and into the terminal of the source. The answer is A, positive, negative.
Positive to negative. Makes sense.
Yep. Okay, question 5. According to the current flow theory, Joseph J. Thomson discovered that electrons flowed from the negative terminal of the source toward the positive terminal of the source. The answer is B, electron.
Electron current flow theory. Yeah, that's the one that's actually right.
Right. Question 6. According to the electron current flow theory, Joseph J. Thomson discovered electrons flowed from the terminal of the source toward the terminal of the source. The answer is B, negative, positive.
Negative to positive. Yeah, that's how the electrons actually move.
Okay, question 7. To create current flow in an electrical circuit, a ocean is placed in the circuit to supply the energy needed to cause electrons to leave their atom and move to other atoms through the circuit. The answer is C, power source.
Power source. Makes sense. That's what gives the electrons the push they need.
Exactly. Okay, question 8. A battery is an energy source constructed of one or more voltaic cells. The answer is A.
Chemical.
Chemical, yeah. It's all about chemical reactions happening inside.
Yep. Question 9. A is constructed with an electrolyte, a negative terminal, and a positive terminal. The answer is D, battery.
Battery, those are the three main parts.
Yep. Question 10. Chemical activity in the directional causes a buildup of electrons at the negative terminal, creating the energy necessary to move electrons within a circuit. The answer is A, battery.
The battery, right. That's where the chemical reactions are happening.
Right. Question 11. Electrons in a battery leave the negative terminal and return to the positive terminal, always traveling in the same direction. This is known as current. The answer is B, direct.
Direct current, or DC, always going one way.
Yep. Question 12. Most electrical energy is generated using A, which creates the energy necessary to move electrons within a circuit. The answer is A, electromagnetism.
Electromagnetism, that's what the generator's right. Yep, the spinning magnets and coils of wire. Question 13. Photoelectricity is the conversion of energy into electrical energy, which creates the energy necessary to move electrons within a circuit. The answer is A, light.
Light. That's how solar panels work.
Exactly. Question 14. Thermoelectricity is the conversion of energy into electrical energy, which creates the energy necessary to move electrons within a circuit. The answer is D, heat.
Heat. With the thermocouples and stuff.
Yep. Question 15. A common application of thermoelectricity is a SET, which is a sensor that measures temperature. The answer is D, thermocouple.
Thermocouple. Okay, that's a tough one.
I know, it's a weird word. And finally, question 16. Piezoelectricity is the conversion of or vibration into electrical energy necessary to move electrons within a circuit. The answer is B, pressure.
Pressure, like squeezing a crystal.
Exactly.
Whew, I think we got all of them right.
I think so too. So there you have it.
The mysteries of electricity revealed.
Yeah. We've covered a lot of ground today, from the basic components of a circuit to all those different ways of generating electrical power.
It's really amazing to think about all the different ways we can make electricity work for us.
And it's clear that a power source is the key to it all, the thing that gets the electrons flowing and makes everything run.
No power source, no electricity.
Exactly. So as we wrap up our deep dive here, one final thought for you to consider. Think about the impact of these different power generation methods on our world. And what might the future of electricity look like as we try to meet our growing energy needs in a sustainable way? It's something to really ponder. Thanks for joining us on this electrifying journey.